Hello and welcome to my channel. Today I am going to discuss fluid mechanics by exploring Reynolds number and flow regime for pipe flow, and I'll solve one numerical problem on Reynolds number. Let's get started. So here is the Reynolds number definition. So Reynolds number is a dimensionless quantity used to predict fluid flow pattern in different situations. It is defined as the ratio of inertial force to viscous force within a fluid flow. It is instrumental in predicting the transition between laminar and turbulent flow regimes. The expression for Reynolds number is given by Re is equal to rho Vl by mu. So here rho is density of the fluid, that is in unit, that density of fluid unit is kg per meter cube. V is the velocity of the fluid, that is meter per second, and L is the characteristic length meter, and mu is the dynamic viscosity of the fluid, that is Pascal second, means the unit of dynamic viscosity, that is Pascal second. Now we know that Reynolds number is nothing but inertial force by viscous force. It is the ratio of inertial force by viscous force. Now what is inertial force? The inertial force is given by, that is Fi, mass into acceleration. So we know from the Newton law of viscosity or Newton second law of motion. So mass into acceleration. So here mass is nothing but rho into volume, density into volume, and acceleration we know the velocity by time. So now here that rho is as it is, the volume is nothing but area into length and into velocity by time. Now if I reorganize, so rho, then area, then length by time, and then into multiplied velocity. So here length by time is nothing but velocity, so it will be rho into area into velocity. So rho a v square. So where a is the cross sectional area. Okay, so now we got inertial force. Now coming to the viscous force, the viscous force Fb is given by, we know that tau is shear stress and du is the velocity gradient. So here that viscous force from the Newton law of viscosity, shear stress is directly proportional to velocity gradient. So here viscous force we can easily get that shear stress into area. Shear stress is nothing but mu into du by dy into area. So here mu is as it is, and from that two parallel plate problem we know that du by dy we can write as a v by l into a. So here the Fb will be mu into v by l into a. Now we know that by the definition of Reynolds number, that inertial force by viscous force. Now we plug all this value and finally we will get Reynolds number is nothing but rho Vl by mu. Now for the Reynolds number in pipe flow, in the case of pipe flow, the characteristic linear dimension L is taken as a diameter of the pipe d. So Reynolds number becomes that rho Vd by mu. So here rho is the density, V is the velocity of the fluid and fluid flow, velocity of the fluid, and d is the diameter of the pipe, and mu is the that fluid dynamic viscosity. Alternatively, we can also write Reynolds number using kinematic viscosity. So we know kinematic viscosity nu is nothing but mu by rho. So here that mu by rho, that is opposite, so means rho 1 by nu means rho by mu. So that will be Reynolds number is Vd by nu. So where nu is the kinematic viscosity, we know that unit of kinematic viscosity meter square per second. So we know the Reynolds number definition, and we know how to derive the Reynolds number from that inertial force by viscous force, and we got the expression. Now coming to the flow regime for pipe flow. So here that flow regime for pipe flow, so here I am showing one picture. So suppose fluid is flowing through a pipe. Okay, so when that you know that when fluid is flowing through pipe, the flow is like a layer by layer. So when layer is not mixed, it is very smooth flow. Okay, so that is actually called laminar flow. Now when flow is just started to mixed, so that is actually called transient or transitional flow. And when there is a flow is that chaotic flow, so when layer is mixing with each other, so that is actually called turbulent flow. Now from the Reynolds number we can easily characterize the flow regime. So now when we know Reynolds number is nothing but rho Vd by mu. So from that, if we know the diameter of the pipe, that fluid density, fluid viscosity and the velocity. So we can easily calculate the Reynolds number. So when Reynolds number less than equal to 2100, so that is called laminar flow. So when Reynolds number 2100 less than Re less than 4000, so that is actually transition flow, and above 4000, that is turbulent flow. So from the Reynolds number we can easily characterize the flow regime or fluid flow. So what is a real life example? So real world connection is here. So in pipeline design, suppose we are chemical engineering or mechanical or civil, so we can do the some pipeline, we can easily do the pipeline design. So what engineers actually do? Engineer use the Reynolds number to determine if the flow is laminar or turbulent, guiding the selection of pipe diameters and materials for efficiency and safety. So that is the real life example of Reynolds number. Obviously we can characterize the different flow regime. Now we are going to calculate, we can going to solve one numerical problem, or first calculate Reynolds number and then we can determine the flow regime. Now here is the problem statement. So here diesel with a density of 0.832 kg per liter and a kinematic viscosity that is 9 centistroke at 40 degrees centigrade flows at a rate of 5 kg per second through a tube with a circular profile and a diameter of 120 mm. Calculate the Reynolds number and determine the flow regime. Now first density is 0.832 kg per liter. Now if we convert liter to meter cube, so we have to multiply 1000. So here from the kg per liter to kg per meter cube, so we have to multiply 1000, so that will be 832 kg per meter cube. Now here nu, that is kinematic viscosity, is given 9 centistroke. So from that 9 centistroke to meter square per second, so that will be 9 into 10 to the power minus 6 meter square per second. So now here that is flow rate is given 5 kg per second, so that is actually called mass flow rate is given, and diameter is given 120 mm. So from that mm to meter, if we convert, so that will be 0.12 meter. Now as here that mass flow rate is given, so from this mass flow rate we have to calculate the velocity. So first calculate the velocity of fluid using the mass flow rate. So we know that mass flow rate is nothing but rho into A into V. So now we know rho, we know pipe diameter, from that we can easily calculate area, and then finally we can calculate V. So here here A is the cross sectional area of the tube. So cross sectional area we know pi into d by 2 that whole square, the pi by 4 d square. So here if we put all this value, and we'll get area is nothing but 0.0113 meter square. Now first and then solve the velocity. So velocity is nothing but mass flow rate by rho into A. So that will be 5 into rho is 832 and area is 0.0113. So from doing the calculation, we can easily calculate the velocity. Velocity is nothing but 0.55 meter per second. So after getting velocity, so now we can easily calculate Reynolds number. Reynolds number is nothing but that V d by nu. So velocity we know, d is we know, and that nu kinematic viscosity we know. So after plugging all this value, and if we calculate the Reynolds number, so Reynolds number is 7333.33. So from this value we can characterize what is the flow regime. So we know that Reynolds number greater than 4000 is a turbulent flow. So we can say that flow is classified as a turbulent flow. That's it. Thank you.